Okay, this is the chapter review for chapter 2. We're going to split it up into two sections. Part 1 deals mostly with inorganic chemistry, and part 2 will focus on organic chemistry. So let's get started. And all matter, organic or inorganic, consists of elements. So we've got to start with elements, the very basic building blocks of all chemistry. Chemistry is the study of matter and it's in transformations. And matter is defined as anything that has mass um, or that occupies space. It is composed of elements. Elements are, as I said, they're as basic as they come, and they cannot be broken down to simpler forms except subatomic particles, but then those subatomic particles um, cease to form chemical um, constituents as we know them, right? So they're a different class on their own. Um, and we can arrange all the elements in the periodic table, and which is a list of all known elements, and it's a very useful and systematic way of organizing the elements, and you'll learn all about that in chemistry. Composed of protons, neutrons, and electrons. In the case of hydrogen, you only have one proton and one electron. If you have the same number of protons and electrons, then the element is not charged, or it's neutral. The nucleus is composed by the protons and the neutrons, and you have various amounts of these, and the number of protons defines what element you're talking about. So if you're one proton, you're hydrogen. If you have 8 protons, you're oxygen. And if you have 11 protons, you're sodium. Generally, you have the same number of protons and neutrons, but you can have different isotopes that have different number of neutrons, and that can vary. Some isotopes are stable, some are not. The electrons contain a negative charge, but they have very little mass, almost unappreciable mass, very little, and they orbit these shells. Here's one shell for hydrogen, 2 shells for oxygen, 3 shells for sodium. So they're found in these electron shells, and the nucleus is in the center of the atom, and they are not composed of shells. There's basically the protons and the neutrons all found together in there. Atoms and elements are symbolized by the atomic symbols, which are composed of either 1 or 2 letters. So these abbreviations are important to know. We're not going to ask about these in detail in this course, but for chemistry and other courses, you will be expected to know the symbols for all the different elements. The atomic number of a particular element is, as we mentioned, the number of protons, so 1 for hydrogen, 8 for oxygen, etc. And the atomic mass is roughly equal to the number of protons, plus its neutrons. As we mentioned, if you have the same number of protons as electrons, then you're electrically neutral atom. I also briefly mentioned isotopes, and so atoms that have of an element that have the same number of protons but have different atomic masses, mostly because of the different number of neutrons, those are different isotopes. And so generally we have the same number of protons as neutrons. And if the number of neutrons vary, you're going to produce different isotopes of that atom or that element. Remember, the element is defined by the number of protons, so that's sort of constant. It's the neutrons that can vary in order to name the different isotopes. Okay, some of the isotopes are unstable, meaning that they decompose over time and give off um, particles, subatomic particles, and these are called radioisotopes. So radioactive material gives off particles, and those are a type of isotopes that are called radioisotopes. So the radioisotopes give off radiation as well as particles. So radiation meaning energy. And this energy can have negative effects on the material around him. But that also means that some radioisotopes have very useful applications in the scientific research field as well as medical uses. For example, C14 can be used to date fossils because a particular compound gives off uh, radioactive particles at a given rate over time, and so by knowing that rate, you can estimate the age of a particular carbon-containing compound. Radioisotopes are also routinely used in imaging in the clinic, as well as to treat cancers, and also to supply power to implants such as pacemakers. You have to think about chemicals and chemistry and materials as um, the sources of energy to supply the fuel for life processes or life activities. And so energy contained within compounds is the capacity to do work. So all mass has an energy associated with it, as described by Einstein's famous formula, E equals mc squared. So mass and energy are related. The amount of energy that is stored in a chemical bond or chemical forms, this is known as potential energy because it hasn't been converted yet. Kinetic energy, on the other hand, is energy of motion of molecules. And this is energy that's available to do work. And both of these forms of energy can be transformed into one another. And a lot of biochemistry has to do with this back and forth transformation. You can think of the electrons in an atom as having potential energy. Okay, and so every shell in which an electron is found is like a specific level of potential energy. The farther from the nucleus a given electron is, the more potential energy that those electrons have. All atoms are most stable when their outermost shell is full. And this is an important driver of chemical reactions because atoms want to interact with other atoms so that they can fill their outermost shells, so they can achieve the most stable conformation. So this is key to understanding a lot of the chemical reactions that happen in your body and elsewhere. When two atoms or chemicals come together, they can create chemical bonds. And these bonds are attractive forces that hold the atoms together. And there are various types of chemical bonds. There's covalent bonds, ionic bonds, and hydrogen bonds. And these are all very important to understand biochemistry. In covalent bonds, what you're going to have is atoms that are sharing electrons. So some of the electrons that are spinning around these nuclei of these atoms are being shared, meaning that they're part of both interacting compounds. These are typically the most strong of the bonds, or very strong bonds. Example of is the hydrogen bonding, right? Or here's a double, just a single bond for hydrogen. Or a double bond between two oxygen molecules, or the bonding that happens between the two hydrogen atoms and oxygen in a water molecule. So these are strong bonds that are difficult to break. There's different flavors of covalent bonds that are important to consider. You have nonpolar covalent bonds. If the electrons are shared equally, this is the situation. So for example, hydrogen, oxygen, methane, and many others are neutrally bound molecules. They form nonpolar bonds, so there's no charge in either of these. There's no appreciable charge. On the other hand, polar covalent bonds, the electrons are not shared equally. A good example of this is water, very important for life, right? Water has unequally shared electrons because the oxygen has a stronger pull on the electrons than the hydrogen gas. That means that the hydrogen atoms in the water molecule tend to be more positive than the oxygen. Excuse me, because those negatively charged electrons are closer to the oxygen molecule. Here's a picture, figure 2.5, describing this situation. So here you go, hydrogen, a single covalent bond. Here's equally shared electron shells, outer shells. Here's oxygen, same situation, equally shared. Both nuclei pull equally on these electrons, on these negatively charged electrons. And so they are shared equally. Now consider oxygen. Oxygen has a, because of the characteristics of the atom, tend to pull those electrons a little closer to the oxygen. And so there tends to be a very slight positive charge around the hydrogen side of the molecule and a slight negative charge on the side of the oxygen. I'm putting these in parentheses because they're not full charge, they're just partial charges. So oxygen tends to be a little more positive, and the hydrogens tend to be somewhat more positive. So sorry, oxygen a little more negative, and the hydrogens a little more positive. Okay. Compare covalent bonds with ionic bonds. And in this case, you have two atoms that are charged that come together to form an ionic bond. Okay, so these are oppositely charged ions. How do you get a charged ion? Well, if positively charged ion forms if an atom or molecule loses electrons. So if you lose negative charges, you become more positive. On the other hand, a negative charged ion forms when it gains electrons. So you're adding negative charges to that compound, so you become more negative. When you have a negatively charged ion come together with a positively charged ion, those negative and positive charges attract and you form an ionic bond. A good example of this are salts, such as sodium chloride or table salt. Sodium, being positively charged, and chloride being negatively charged are held together by those ionic forces that attract those two atoms together. So here's an example of that, figure 2.6. So you can see sodium ion has this extra lonely electron here on its outer shell, and chloride, or chlorine atom, is missing an electron on its outer shell. So this is a very strong drive that makes this unstable electron jump to a very stable conformation to the chloride molecule. So if sodium loses an electron, loses that, it becomes more positive, and that electron is gained here by the chloride atoms and becomes negatively charged. So sodium positive, chloride negative. These two oppositely charged ions now attract each other, and it forms an ionic bond. Another important type of bond is the hydrogen bond. And these form between polar molecules. And remember, polar molecules are those that contain polar covalent bonds. So there's an equal sharing of electrons, such as the water molecule that we talked about. Or even if they're electrically neutral overall, but have an uneven charge distribution among the molecule itself. So you can imagine a large molecule here. I'm going to draw it, kind of this bumpy protein, large bumpy protein. And maybe there's a slight negative charge here, and a slight positive charge here, and another slight negative, and another slight positive part here. And so if you count these, there's two positive charges, two negative charges. So we say that this molecule is electrically neutral overall, but the charge distribution is uneven. And so this type of molecule or compound could engage in hydrogen bonds as well. So this hydrogen bond is a weak attraction between oppositely charged regions of polar molecules. A good example of this is the forces that keep water molecules together. So if we go back to our example here with water, you might have another oxygen, another water molecule here with oxygen and its two hydrogens. And these slight negative and positive charges can form hydrogen bonds. So here's an example of a hydrogen bond. It's not a covalent bond. It's not an ionic bond because hydrogen and oxygen here are not totally fully charged atoms. They're only partially charged, and they form what are called hydrogen bonds. The reason why they're called hydrogen bonds is because hydrogen is very commonly encountered in these situations because of its characteristic of having an unstable electron that can be easily pulled away from it. And so that's why. These hydrogen bonds, and particularly in the case of water, are very important. So here are in the dotted lines are those hydrogen bonds. And that gives water a lot of its physical and chemical properties. So it's one of the reasons why water is found in liquid at room temperature, because the attraction of forces of these hydrogen bonds keep these water molecules from being lost and drifting away in terms of us in the form of gas, right? It also means that ice can form, or different type of crystal characteristics form, because of the nature of these bonds that form among groups of these molecules. When we look at living organisms, we see that most of what's in our bodies is only a few certain elements. Now, 99% of the body weight is 6 elements alone: oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. In fact, these 2 are mostly in the form of bones and other inorganic constituents, mostly. These make the bulk. Oxygen, carbon, hydrogen, and nitrogen make the bulk of our bodies. Water has lots of important characteristics that make it very important to sustain life. It is the main solvent in which substances in our body are dissolved in. All those substances are known as solutes, and but they're not all made equal. There's some compounds in our bodies that are very hydrophilic, meaning that they are able to dissolve in water quite readily, quite easily. And these are typically polar molecules. And because the water has a slight charge to it, right, because of those hydrogen bonds, polar molecules can be easily attracted to those water molecules, and therefore the 2 interact very easily and become dissolved. Compared with hydrophobic compounds such as fats and lipids, these are non-polar, neutral molecules, and so it's very difficult for them to interact ionically with water, and so that means that they're not dissolved very well in water. So those are 2 important contrasting major groups of compounds in your body, solutes in your body: hydrophilic and hydrophobic. Polar compounds such as sodium chloride and most salts. Water also is important because it can remain liquid at body temperature. So it's the most important transport solute in the body. Your body is 90% water to be able to do that. It's a major component of intracellular spaces, so within the cells, inside the cytoplasm of cells, as well as the extracellular spaces. In fact, 60% of your body weight is water, so that's quite a lot. And a very important characteristic, and this goes back to our topic of homeostasis and using the example of temperature regulation. So water is going to be crucial in regulating body temperature. Okay, so water can absorb a large amount of heat energy, and this means that this prevents rapid changes in body temperature. What this means is that water can absorb a lot and hold a lot before any temperature change can happen. It can absorb a lot of heat. You have to put in a lot of heat in water to see a given increase in temperature. Same goes the other way around. You have to remove a lot of heat before you can see a decrease in temperature of a body of water. This also means that when water evaporates from your skin, it removes a lot of heat from the surface of your skin. So evaporative cooling is a very important mechanism by which your body loses excess heat very efficiently. Water is also important to understand because it participates in a lot of chemical reactions. For example, when you synthesize carbohydrates, when you put together large molecules such as carbos and proteins and lipids and large organic molecules, this will produce water. So, and so this can be an important source of water in our bodies. On the other hand, when you break down carbohydrates, proteins, and lipids, this typically consumes water. The reactions in general that are involved in this are what are called hydrolysis reactions, and these require water. Another important characteristics of aqueous or watery solutions is the importance of hydrogen ions. So there's always going to be some hydrogen ions that are loose in a particular aqueous or watery solution. Compounds that give off a lot of hydrogen into solution are called acids. So these donate hydrogen ions to the aqueous environment. This increases the hydrogen ion concentration, which is going to bring down the pH. It's going to make something very acidic. Bases, on the other hand, are compounds that when dissolved in water remove hydrogen. So they remove it. Negative sign here for removal. Acids add hydrogen ions to the solution. Okay, here we go. That's a little better. All right. Bases remove hydrogen from solution because they accept the hydrogen ion, so removing them from the solution. So this decreases the hydrogen ion concentration in the solutions, making things more alkaline. So increases the alkalinity. Okay, so we use a scale to measure how many hydrogen ions are found in solution, and that is the pH scale. So a measure of hydrogen ion concentration in an aqueous solution. The pH scale ranges from about 0 to 14, 7 being neutral. Here, 7 being neutral. If you're less than 7, then you're acidic. Okay? You're less than 7, you're acidic. This means that you have a lot of hydrogen in solution. There's a lot of hydrogen. The concentration of hydrogen is high. You have a low pH, a very acidic pH. And if you have very low levels of hydrogen, you form a basic solution or an alkaline solution, and your pH is greater than 7. Figure 2.1, or sorry, figure 2.10 shows the scale here, and you can see that overall most of our bodily fluids hover around the neutral range. And by the way, our bodies are this is something that's also homeostatically regulated. And so our body fluids are maintained within a very narrow range of pH. More alkaline means more basic, means less hydrogen ions, right? And if you have more hydrogen ions, you become more acidic. And the pH goes down. Maintaining a constant pH in our bodies is very important, and there's many aspects of our body, a lot of physiological processes that help maintain pH. But one of the things that is found in our watery environments inside our body um, is the presence of these buffers. Buffers are very important in minimizing changes in pH, and this helps maintain a stable pH of about neutral condition in our body fluids. A very important system that regulates pH is the interaction between carbonic acid and a compound known as bicarbonate. And so here you have when carbonic acid dissolves in water, it gives off hydrogen. That's why it's called an acid. It gives hydrogen, making the solution acidic. That hydrogen will interact and form bicarbonate. And this interaction is, or this reaction is reversible, meaning that it can go back and forth in an equilibrium condition. So if you have a lot of hydrogen, you're going to drive the reaction that way. And if you have very few hydrogens, it's going to drive the interaction this way. Oops. Let me get my eraser. Okay, erase this a little bit to clean it up. All right. Okay, so let's see. If the blood is too acidic, that means you're going to have a lot of hydrogen in there. So that extra hydrogen is going to interact and react with carbonic acid and form bicarbonate. So here's the arrow pointing just one way, right? So meaning that the equilibrium reaction is favored going this way to the right, right? So that removes, as you go this way, you remove hydrogen ions, and that brings the pH of the solution back to neutral. If you were originally starting from a too acidic condition, you go back to neutrality. If you have very few hydrogen ions, you're very alkaline, right? That drives the reaction the other way. So starting with bicarbonate here, it's going to release some of that hydrogen and increase the acidity of the solution, bringing it back to neutral from the alkaline side of things back to the neutral side of things. So if you go too much, then it'll become acidic again, right? And then you'll go back to the other way. So this equilibrium reaction is always occurring in your body, and it's an important way that your body fluids maintain a pH of around 7 or abouts. Okay, and that's it for this part of chapter 2.